So now that we've looked at expanding sums, we want to look at the reverse order. Here we want to look at expressing sums in their sigma notation. So, to write a sum in sigma notation, we must generate a general formula for the kth term. And there's a couple of important things I want you to keep in mind as you're looking at this. So the first thing I want you to remember as you go through these problems and as you practice is that multiple sigma notations may represent the same sum and value. So multiple sigma notations may represent the same sum. So in other words, multiple answers can exist. And we'll explore this in more detail as we look at examples. This first point is related to the second point here as well. So the second thing I want you to keep in mind as you're practicing this is that the general formula, x sub k, is going to change or can change with the lower limit of summation. So the general formula that we're looking for, x sub k, will change with the lower limit of summation. Again, we'll look at this in more detail with some examples here. So oftentimes, it's easiest to start with a lower limit of 0 or 1, but again, keep in mind, any integer value will work. So it's often easiest to start with k is 0 or k is 1, but this is not exclusive. But any integer works. So let's take a look. So here is an illustration of what we're looking at in this section. So we want to express the following sum in sigma notation. So I have 1 plus 3 plus 9 plus 27 plus 81 plus 243. And so looking at the given sum here, you want to ask yourself, do you see any patterns? So looking at this, we realize, wait a minute, we're given the sum of the powers of 3. So we're given the sum of the powers of 3. So let's rewrite this sum so we can really appreciate this. So again, we have 1 plus 3 plus 9 plus 27 plus 81 plus 243. And we know anything raised to the 0 is 1. So if we have 3 to 0, we would get 1. If we take 3 and raise it to the first power, we get 3. If we square 3, we get 9. If we cube 3, we get 27. If we raise 3 to the fourth, we get 81. And then 3 to the fifth is 243. So we can see that we have the powers of the sum of the powers of 3 specifically from, we look at our first term, so this would be starting at k is 0 and ending at k is equal to 5. So we can now go ahead and rewrite this in its summation notation. So therefore, the summation notation, or your sigma notation, for this sum is going to be equal to the sum from k is 0 to 5. And then again, notice looking back at our sum here, what is changing? It's the powers that are changing. So that's where the kth variable will go in our general formula. So we can say that this is 3 to the k. And again, it's always a good idea here, even if you're 100% sure that, yeah, this is the right summation notation, it never hurts to plug it back into your general formula just to make sure. And so when we plug these terms back in, we are confirming to ourselves that, yes, okay, we're right, we're good. Now, this is not an exclusive solution. This is one of infinitely many solutions. So what I'd like to do with you now is think about, well, what if we change the lower limit? So let's think about how the general formula is going to change if we change that lower limit. So how does this summation change, or how does this sigma notation change if, and we'll look at a couple different cases here. So case 1, how is this going to change if we start at k as negative 1? So how will the sigma notation change if we start at k as negative 1? So let's keep in mind here that we still, looking back here at our sigma notation that we just found, we still want our new sum, our new sigma, to generate a first term of 3 to the 0. So we still want the first term in this sum to generate 3 to the 0. So what are we going to need to do to our general formula to attain this? Again, looking back at our original answer here, we're starting at k is 0 and going to k is 5, and our general formula has 3 to the k. So in order for our new sigma notation to still generate this, we're going to need to add 1 to the k in the general formula. So what do I mean? I mean that we can take that answer we just found, the sum from k is 0 to 5 of 3 to the k, and we can rewrite this in an equivalent form, the sum from k is negative 1 to 4, and the general formula, because we decreased our lower limit, the k in the general formula has to increase proportionally. So this is an equivalent answer. So what this is showing us is that if you decrease your lower limit, you need to increase the k in the general formula. So with that being said, let's now think about, okay, well, what if we go in the reverse direction? So what if we start at k is equal to positive 1? And again, we want to keep in mind here that we still want the first term in our sum to generate 3 to the 0. So here, because we're increasing from k is 0, we're going to need to subtract 1 from the k in the general formula. So from k in our general formula, x sub k. So what I mean we'll take this original answer that we have the sum from k is 0 to 5 of 3 to the k. And if we take this sum and we increase that lower limit to 1, then the upper limit must be increased by 1. But the general formula, the k of our general formula, must decrease by 1. And again, if you're unsure if this is really going to give you the same answer, I encourage you to check, right? It never hurts to double check. Right, so if we did this with our first case here, we're starting at k is negative 1, so this would be 3 to the minus 1 plus 1, plus 3 to the 0 plus 1, plus 3 to the 1 plus 1, plus 3 to the 2 plus 1, plus 3 to the 3 plus 1, I just ran out of room, plus 3 to the 4 plus 1. And now, so there's your expansion. And when we evaluate this, we have 3 to the 0 3 to the first, plus 3 squared, plus 3 cubed, plus 3 to the fourth, plus 3 to the fifth, which matches. It's equivalent. And we can do the same thing with case 2. But if we wanted to confirm that, is this really, truly equivalent? Plug the values in, expand it out. So now we have 3 to the 1 minus 1, plus 3 to the 2 minus 1, plus 3 to the 3 minus 1, plus 3 to the 4 minus 1, plus 3 to the 5 minus 1, plus 3 to the 6 minus 1. Again, we can see here that, yes, our algebra is correct. 3 to the 0, plus 3 to the first, plus 3 squared, plus 3 cubed, plus 3 to the fourth, plus 3 to the fifth. So all 3 of these answers here are equivalent.